When you think about the International Space Station, what comes to mind? For me, it's this incredible symbol of human cooperation, right? Our home in the stars, just floating 400 kilometers up there. But here's the thing. It's also a machine under constant assault. I mean, it's facing challenges that are just almost impossible to wrap your head around. And to really get a sense of just how fragile this outpost is, we've got to go back to one very specific, very tense day.
So the date is March 23rd, 2012. Up on the station, it's pretty much business as usual for the crew. They're running experiments, doing maintenance, the normal routine. And then a call crackles in from Mission Control.
6 minutes. That's it. That is all the warning they get. Houston is tracking a cloud of space debris and it's heading right for them. There is absolutely no time to move the station. The only thing the astronauts can do is scramble to their Soyuz escape pods and just hope for the best.
So that near miss really makes you think, doesn't it? It brings up this massive question. How on earth do you protect a machine this big from a threat moving that fast? How do you keep this incredible laboratory, the size of a football field, safe when it's literally flying through a cosmic shooting gallery 24/7?
Okay, so before we can even dive into the amazing solutions the engineers came up with, we first have to get our heads around the sheer scale of this thing. Because we're not talking about some tiny little satellite or a capsule here. No way. This is a structure that's almost unimaginably big.
All right, get ready for this number. The International Space Station weighs in at 460,000 kilograms. Now, that's just a huge number, right? So let's try to put that into perspective.
Yeah, that's like taking 380 cars, or maybe think of it as 25 big city buses, and launching all of that into orbit. It's a staggering feat of engineering just to get that much mass up there.
And the cost? Oh, the cost is just as mind-boggling. This is, by a huge margin, the most expensive single thing humanity has ever built. We're talking over $150 billion, and that number keeps climbing. It's a monumental investment from countries all around the world, all for the sake of science and pushing our boundaries.
Now, you can't just launch a giant like this in one go. Of course not. It was born out of this incredible new era of cooperation between the US and Russia after the Cold War, and they built it piece by painstaking piece, module by module, right there in the vacuum of space. And maybe the most amazing fact of all, since the year 2000, someone has always been on board. It has never been empty. A constant human presence out there in the void. All right, so we've got this massive station orbiting the Earth. Now for the first, and maybe most obvious, life or death problem, breathing. There's no air in space, right? It's a vacuum. So how in the world do you give the crew a constant, reliable supply of oxygen when they're 400 kilometers away from the nearest breath of fresh air?
Well, you can't just keep shipping it up from Earth. I mean, the crew needs something like 200 kilograms of fresh oxygen every single day. And when a single cargo rocket costs around $200 million, well, you can see how that's just not going to work long term. Nope, the solution had to be self-sufficient. It had to be generated right there on the station.
And the answer they came up with is this beautifully simple and elegant chemical process called electrolysis. The basic idea is to take water, good old H2O, and use electricity, which they get from the solar panels, to split it back into its core components, hydrogen gas and that all-important breathable oxygen.
But of course, there's a catch. This whole process works great on Earth, but in zero gravity, it's a whole different ballgame. You see, here on the ground, those little oxygen bubbles are lighter than the water, so they just float to the top. Easy. But in space, they just kind of hang out in the water, all mixed together. So the solution is pure genius. They built a centrifuge that spins the whole mixture really fast. This creates a kind of artificial gravity that forces the heavier water to the outside, which lets them collect the pure, lighter oxygen gas from the center. It's just such a clever piece of engineering, and it's what makes the station's air supply sustainable. Okay, so the crew can breathe. That's a big one checked off the list. But what about those space bullets we mentioned at the beginning? The station is constantly, and I mean constantly, flying through a swarm of tiny micrometeoroids and all sorts of man-made junk.
And this is where things get really terrifying. The ISS is screaming through space at 27,000 kilometers per hour. At that speed, a single grain of sand hits with the force of a car crashing into a tree. A tiny fleck of paint becomes a lethal bullet. A hole in the hull isn't just a leak, it's a catastrophic depressurization event. It's an ever-present danger.
So how do you survive that? Well, you give the station a bulletproof vest. It's this incredible multi-layered shield. The very first, outer layer, is super thin. It's designed not to stop the particle, but to make it explode, to shatter it into smaller, less dangerous pieces. Then there's a middle layer, this woven composite fabric that acts like a shock absorber, soaking up the energy from that shrapnel. And only then do you have the final, inner pressurized wall. It's this layered defense that has kept the station safe from these tiny bullets for decades.
But that vest, as amazing as it is, only works for the small stuff. For anything bigger, say the size of a marble or larger, the station has to get out of the way. It has to move. But think about it. How do you steer a 460,000-kilogram behemoth without constantly firing rockets and burning through your precious and very limited fuel supply? Well, the answer is one of my favorite bits of engineering on the entire station. It's a technology that uses, get this, zero fuel. None. They're called control moment gyroscopes, or CMGs. And no, these are not thrusters. They're basically 4 massive, heavy flywheels that use the fundamental laws of physics to turn the entire station.
You can actually feel this principle yourself. If you've ever held a spinning bicycle wheel by the axle and tried to tilt it, you feel this weird, powerful force pushing back at you, right? That's angular momentum. The CMGs do the exact same thing, just on a colossal scale. These 4 flywheels are spinning at over 6,600 revolutions per minute. When they need to turn the station, they don't fire a rocket. They just use motors to tilt these spinning gyros. That powerful force gets transferred to the body of the station, and the whole thing, the whole football field-sized structure, rotates. It's incredible. They are literally steering with physics, powered only by the sun.
So, okay, we've seen some of the absolutely mind-blowing engineering that keeps the astronauts alive and the station in one piece. But this brings us to the biggest question of all. Why? Why go to all this trouble? Why spend all those billions of dollars solving problems that seem, well, impossible? The reason is that the ISS is so much more than just a science lab in orbit. It's our training ground. It's our dress rehearsal for deep space. It's where we figure out how to live off-planet for the long haul. Every single one of these systems, making oxygen, recycling water, steering without fuel, is a critical test for the kind of self-sufficient ships and habitats we're going to need for a trip to Mars. Every experiment studying what zero-G does to the human body gives us crucial data to keep astronauts safe on journeys that will last years, not just months.
Ultimately, the ISS is proof. It's proof that humanity can come together and solve problems that seem completely impossible. It is our very first permanent home off-planet, a tiny tentative foothold in the cosmos. And every single lesson we learn up there is paving the way for the next giant leap. Which leaves us with just one really exciting question. Where will our next home be?